So now we're going to look at something called a distinguishable permutation. And we have a distinguishable permutation when some of the items are like. So by switching places, they make no difference. So in this case, we have, over on the right, we have boxes P, Q, and R. They all represent one kind of object. N is still going to be our total, like it was before. And then this is the formula that we're going to use for distinguishable permutations. Now, in this scenario over on the right, there's three options, P, Q, and R, but you could have infinitely many. There's no fixed number. It could be 2 different groups. It could be 10. So however many you have, you take the factorial of each and you divide. Also, when you divide, please note that you must put that denominator in parentheses when using your calculator. So let's look at an example and make a little bit more sense of this. So Iris is planting 11 colored flowers in a line. In how many distinguishable ways can she plant 4 red flowers, 5 yellow flowers, and 2 purple flowers? So basically what this means is if I have 2 purple flowers and they're in a row and I switch their places, it doesn't change the order. The purple is still where the purple was. So this is how you can determine a distinguishable permutation versus a regular permutation. So the first thing we want to do is say, okay, well, what is my N value? So it said we had 11 flowers, and even if it didn't say how many flowers we had, just add 4 plus 5 plus 2, and that gives you your 11. So your total. So my equation would be 11 factorial over 4 factorial times 5 factorial times 2 factorial. Again, I'm going to plug this into my calculator and put parentheses. Just as a note, factorial in the calculator is stat probability just like the other ones, except it's number 4. So that gives you that exclamation point as you enter in this equation. And when you do that, we have 6,930 different options. Something else is that dividing makes the number of permutations smaller. So if we had 11 and they were 11 different colors, that number would be greater than 6,000. But once you divide by the groups of colored flowers, then that number comes down. Okay, so let's look at the next example. Find the number of distinguishable arrangements of all of the letters in the word marmalade. So the first thing we're going to do is identify all the different letters. So we have M, A, R, M repeats, we've already included that. A repeats, L. A repeats, D, and E. So let's identify how many of each letter is in this word. So we have 2 M's, 3 A's, 1 R, 1 L, 1 D, and 1 E. So our N value here is all of those letters added up, which is 9. So my equation is going to be 9 factorial divided by 2 factorial times 3 factorial times 1 factorial times 1 factorial times 1 factorial times 1 factorial. Now, again, this is an example where we have more than just 3 options or 2 options. We have 6. Again, you're going to put it in parentheses. But to save you, remember on the worksheet we've completed before that 1 factorial equals 1. So let's simplify this in the calculator and write 9 factorial over 2 factorial times 3 factorial in parentheses. And when you do this, you get 30,240. The last part of this section is combination. So the difference between a permutation and a combination is that in a combination, order does not matter. And it's just a group of people versus, first, second, and third place. So note the equation of a combination. It's slightly different than a permutation. The calculator, you get there the same way, except it's number 3 now. So for the first example, 7 choosing 4, we have 7 factorial over 4 factorial times 7 minus 4, which is 3 factorial. So if you plug that in your calculator, again, use parentheses for the denominator, you get 35. Or in your calculator, you have 7 choosing 4, order doesn't matter, and you have 35. So for this next example, same thing. You have 5, that's your n value, choosing an r value of 3, and you get 10. So combinations actually give us a smaller number than a permutation because it's just grouping things together. The order doesn't matter. So we have a smaller number of options. So this first example says you can answer any 3 questions from a total of 4 questions on an exam. In how many different ways can you select the question? Well, it's a combination because it doesn't matter in what order you go. Once you turn it into your teacher, they're not even going to know the order you went in. You just need to answer 3 of 4, any 3 of the 4. So we're going to have 4 total, and we're going to choose 3. And when you plug this into the calculator, you get 4. What if you were selecting 12 of 14 questions? Same concept. 14, and you're choosing 12. After typing it in my calculator, I have 91 options. Example 2. In how many ways can a committee of 3 be chosen from a group of 12 faculty members? So again, it doesn't matter the order we choose them in, they're just a group of 3 people, all equal jobs. So we have 12 faculty members, and we're choosing 3 from that, which gives us 220. And B says, in how many ways can we then choose a department chair, a curriculum chair, and a technology chair from those 12 faculty members? So in this situation, order matters. So once again, we've come back to a permutation. Because there's 3 jobs, and in part A, we also chose 3 people. But these are jobs, so the first person gets denoted to be the department chair. You can't have someone be a department chair and the curriculum chair. So the order of their jobs and how they're picked matters. So it's a permutation of the same values, 12 choosing 3, and you get 1,320 options.